Howdy folks, we're going to get started in just a couple minutes. If I could have people file in up to the front, we've got plenty of seating at the camping chairs. Hello, hello, hello. Hey, if I could have people file into the camping chairs up front. If you're still in the back, we've got plenty of seating up front. We'll be getting started in just a couple minutes. Hey everybody, welcome to the inaugural meeting of Hack AR. Let's give it up for Micah, who's our organizer and tonight's first presenter. As a reminder before we get started, if everyone could please dispose of your plates, cups, and cans. Trash is located directly behind where you got beer and pizza from. Thank you so much.
Okay, there we go. Can everybody hear me okay? A little closer to my mouth. Okay, there we go. Is that a little better? Testing 1, 2. What? Thank you for your patience, everybody. I appreciate it. Must look silly up here. Like, how does this thing work? Thank you so much to each and every one of you for coming out tonight and being interested in augmented reality. It's a big passion for me, and I'm really excited to share it with you. I'm also really excited to share rLoop and what they're doing for the Hyperloop tonight. They're going to come out and they're going to share that. So I'd like to go ahead and welcome up those guys. We have 3 of them here, and they're going to speak tonight. And I'll give you a little rundown on each of them. So there's 3 people. There's Thomas. He's the lead engineer from Hyperloop. There's Merrick. He's part of the controls team. And I'm going to mispronounce his name, even though Alex sent me how to pronounce. Joachim? Oh, okay, great. So if Tom is up here, if you want to come up and join us. Great. Awesome.
All right. All right. All right, I need to find back my password. There we go. All right. Just maybe not in the middle, just, you know. All right, can you guys hear me okay? Yeah. All right. So thank everyone for inviting us here. So we're going to talk a bit about rLoop. That's what we're doing, the Hyperloop crowdsourced project. So I'll talk a bit about what the Hyperloop is for you guys that don't know what this thing is. Quick crash course on the Hyperloop. Then we'll talk about rLoop, the pod called rPod, and the way we do stuff in crowdsourced engineering. So the Hyperloop is a concept that comes from a bunch of different concepts that was, and SpaceX and Elon Musk did a good job at packaging that into one big concept called the Hyperloop. And this is the usual picture for the Hyperloop. So the way it works is, imagine a tube in which you make a vacuum. Inside that tube, you have a pod that is levitating and that you shoot at very high speed inside. The idea behind that is that you have something that can go to very high speed and be pretty efficient, and it's something that is as convenient as a train and as fast as a plane. That's kind of the, in a nutshell, what the Hyperloop is supposed to be. So if you get in some detail, just for you guys to understand what the thing looks like, this is the pod supposed to be for the Hyperloop. You have a cabin, that's the standard aircraft cabin. In front of the cabin, you have a compressor. The reason for that is when you go at high speed inside a tube, even if it's in vacuum, you still need to remove some of the air that is left out. The full system is powered on batteries, so electrical batteries, no fossil fuel. And the whole thing is levitating using either air levitation, so the same type of system you have for air hockey table, or you can use magnets. And the way it's propelled is using linear induction motors. Those are the same type of stuff you find in a railgun, for the one of you familiar with that. The tube themselves, you usually see those tubes that are transparent. Unfortunately, the real Hyperloop, it will probably made out of steel. It's going to be all pretty, you won't see through it, basically. And the idea is to have those things fully solar powered. A fun fact that Joachim mentioned the other day was that if you manage to put solar panel all the way from Los Angeles to San Francisco, just on the top of the tube, you will actually produce more energy that you will need for the Hyperloop. So as you can see, there is a lot of challenge. You can find there is a lot of problem with the system, right? And you can pick any of the ones that are on the screen here to say, okay, this thing will never work. Just why spend some time on it? But there is no real showstopper. And I say, for optimists, of course, you can pick any of those things and say that'll never work. But you don't need to reinvent the laws of physics to have that thing work. You just need to be a bit smart about it and see what you can do. So that's kind of the philosophy we came up with. So in 2015, last year, SpaceX, in order to kickstart the Hyperloop R&D, they proposed to do competition. The way it works is they said, create a team, design a pod, we select the best design, and we'll allow you guys to build a pod that we will shoot down a track that we are a tube that we'll be building in California. So that was the general guidelines. At that moment, I'm losing my voice, I'm sorry about that. I sound like a young kid. At that moment, on Reddit, someone posted this message. Hey guys, let's create a Hyperloop team, which is pretty ambitious, right? You know how stuff works on the internet. So yeah, let's do those great things. Everybody's very excited, nothing happens. So here, that post got actually a lot of interest. You had a lot of people chipping in saying, hey, I'm a mechanical engineer. I can help you guys with some stuff. Hey, I'm a software developer. I'm an embedded control engineer. I can help with the controls. Or people saying, hey, I have no technical experience at all, but I can chip in for some of the money if you need. So a lot of interest in that. Thank you. So we started to get organized. We created an org chart and saying, okay, we should have a team for the control, we should have a team for the software, we should have a team for Mac, and people started to apply. People started to apply on Reddit, and basically people will upvote the post and say, oh, okay, yeah, it looks like you're good for the job. And voila, that's how the whole team was born in the beginning, and that's how rLoop was born. It started as Reddit Loop, but because using the name Reddit without authorization, we were afraid of problems, so shortened it to rLoop, which is actually much more cool, I think. So that was exactly a year ago. That was in June 2015. That was exactly a year ago. And 12 months later, we are now a non-profit in California. We have fully open source. Anybody can join, no background check. We don't ask anything. It's a full hobby for everybody. You can join anytime. We have more than 300 members right now. We have more than, over the lifespan of the project, we had more than 800 members. So people are coming and going all the time. 40 members are the core team, so the people have been there since the beginning. We're doing everything on Slack. That's where we do all our stuff. We have people from all around the world. We're working literally around the clock. We have people on every continent. So that's how we've been doing our stuff. So going back, just when we created the team, this was the schedule, that the stuff we had to deliver. Basically, as you can see, there was a milestone for every month. It started at 1,800 teams, and milestone after milestone is scaled down to 120 teams left. From those 120 teams, they were selected to go to the design weekend in January this year in Texas. The idea was that everybody that was selected get a booth. You have 80 judges, and you have to show your technology, explain your technology, and show why your system was the best. And the judges will give score. There were 60, half of them were non-students, half of them were student teams, so MIT, Berkeley, all those big names. So all the stuff you saw, so I kind of fast forward there, but like 6 months, that in January, that was 6 months of development. All the design was pretty much nailed down, and everything was done online. We never met in person a single time to do this design. Everything was done without exchanging a single email. Everything was done on Slack. So we've been working with those guys like every night after work. We've been exchanging a lot. So it really seems like, you know those guys. You never met them. You know those guys, my friends from the internet. And it's not those kind of friends, but it was weird because we kind of knew each other forever, but never met each other in person. So the first time we met, it was like, oh, okay, yeah, I recognize your face, I saw your picture, but you're actually much taller than I expected, and stuff like that. Oh, your voice is totally not what I expected. So this is the first ever picture, the first picture of two rLoop members ever meeting. This is Amir, is in the room over there, is the NumSim guy, is the lead for the numerical simulation team. He's actually from India. He flew all the way to the competition there. And this is Eric, is our video guy from San Francisco. And
it was like 2 days before we presented the design.
yeah, he just met for the first time just before we presented. This is our happy booth. So a bunch of people that never met before, except on the internet, defending our colors with our fancy rLoop t-shirts. And the logo was crowdsourced also with our guys. Everything was crowdsourced, all the stuff we did. Everybody has a piece to the puzzle. You had one guy that can had no technical skill, but hey, I can make you guys some kick-ass banner and some logo and some mugs. Hey, sure, do that. And voila, that's what we had. So just on the picture here, you have someone from the UK, you have someone in San Francisco, Canada, New York, Belgium. You have pretty much every nationality. And we managed to win the only non-student award they had. So only 30 teams were able to win. There were 20 awards, 23 awards, 22 for student and 1 for non-student, and we managed to get it. So very, very happy about that. That's our happy picture. We got an award which is basically a piece of the alloy that will be used to make the tube for the Hyperloop. And Elon Musk was there, so he autographed our awards. We have a piece of Elon Musk now with us.
Cloning him, don't worry.
So that's, yeah. So what did we win exactly? Well, we won that prize, but we won the right to build a pod, to go ahead with our design and race it on the track in Southern California. So this is an idea of what the tube will look like. I'll get the next couple of slides, get in some details of how the pod works, because I think it's important for you guys to understand some of that. So this is the tubes. This is what SpaceX is going to build. So steel tube. At the bottom of it, you have a concrete slab. On top of it, you have I-beam in the middle that you can use for control or other stuff. And side by side on it, you have plates of aluminum running. And using those for either levitation will be air bearing or magnetic levitation. And this is our pod. This is the concept of our pod. The design, yeah, Soren is one of our sponsors. This design was made by a guy in China. A guy is doing great stuff in China from rLoop. And yeah, we see our main sponsor, which is the T connectivity. So what's behind that system? So this is what it looks like on the inside. You have a pressure vessel. That's the thing you see here on the top. And on the bottom, you have the propulsion substructure. So in the pressure vessel, you put all the stuff that you need that cannot go in vacuum. So all the electrical system, the batteries, a bunch of other stuff that goes in there. You will have also a crash test dummy inside the pod. That's a requirement from SpaceX. They will put a bunch of sensors to see how our pod is doing. You can see the batteries front and top, like pretty heavy and powerful LiPo batteries and our electrical nodes. And the batteries are mainly used for our levitation. And for levitation, we are using Hall-Back arrays from Axpax. So Hall-Back arrays are magnets that you put on a motor. And if you make that motor spin very fast, and you make it spin over a conductive surface, like some aluminum and copper, you create some current in the surface, you create an electromagnetic field, and that will create levitation in the system. So you can see here the type of engine we are using. They are from Axpax in Los Gatos. They're using those engines right now to power the hoverboard. I actually rode on that thing. It's extremely cool, extremely smooth also. And you can see this is the bottom substructure. You can see we have 8 engines for that, those round shaped. For braking, we're using eddy brakes. Those are the things in the middle there, just right there. There we go. Those working in 3D. So eddy brakes is basically a bunch of magnets that you bring close to the I-beam, and when you go at high speed, is the same system. When you go to high speed, if you get that close, you create a magnetic drag. It's the same type of stuff you have in roller coaster. On a roller coaster, when you slow down very fast, it's actually a combination of that kind of brake and the normal brakes, kind of you have in the car. We have a bunch of other stuff. You can see some wheels we're using for backup in case the levitation fails. We have alignment wheels, and we have all the control. We have a lot of Raspberry Pis and Teensys we're using for controls. And for that part, I will let Marek and Joachim talk. So, there you go.
Right. Thank you, Tom. So, hi everyone. My name is Marek. I'm coming from Krakow, Poland, but I live in Geneva, Switzerland, where I work at CERN. I'm a mechanical and controls engineer, and at rLoop, I'm the controls team leader. So, due to the fact that this is the software event, I'm gonna make a very brief introduction to the software that we have and to the hardware that we have to run that software. Just to make a quick distinction, basically what I am responsible is the real-time part of the software, and Joachim is responsible for the non-real-time part of software. So basically he's going to work on the Raspberry Pis, I'm going to work on I'm already working on the Teensys. Our architecture is based on something which is called Node, and it consists of the Teensy plus it consists of the Raspberry Pi. They both are connected using the I2C protocol, and they're all connected together. The Teensys are connected using the CAN bus, which is the control area network. This is something that you can find a lot in automotive solutions, and is used basically for the embedded systems. Tom, can you go further? Right. So what we use that for? So we've got a bunch of stuff that we need to control in real time, and it has to act extremely precisely in a time manner. And we've got all of them devoted to doing preferably just one task. So for instance, we've got something which is called command node, and this is devoted only to controlling the hover engines. We're going to have 8 of them, and it's going to be the same code running to control that. The next thing that we have is the gimbal node, and the gimbal node is used basically for rotating the hover engines around one axis, so that we can get some thrust, or we can actually have some braking force. The next thing that we have is the control node, and the control node is basically responsible for obtaining 6 degrees of freedom parameters. So this is going to be roll, yaw, 3 translations, and we all use that basically to orientate ourselves inside of the tube.
So know which way it's pointing, basically.
Yeah, and one of the most important things basically is that we know how far from the end of the tube we are. You have to remember that we're going to reach a speed of 300 miles per hour. That's basically our goal, and we have to brake. And yeah, that seems like an obvious task, but trust me, it's not. There's one reason behind that. Basically, all of the sensors which are there in the market, they're not made for that environment. So you can have a lot of sensors that are going to work only in a specific area, like for instance at certain pressure, but they're not going to work at certain velocities. So it's very I mean, it's not possible to find that will basically fit all of the scenarios. So we have the whole set of the sensors that we use. And there's also stuff like power node, which is responsible for our batteries. Actually, the hover engines, they're consuming a lot of power.
No.
So it is a very demanding task, and we are putting like a lot of effort into making sure that we're not going to have any fire, because that will be a spectacular failure.
What they call a rapid out-schedule disassembly.
I think in this case, if we don't hit the end of the tube, it will be very slow and painful.
And we're going to have cameras in us, we're going to watch it.
Yeah, so, and that will make Elon sad. We don't want that. So exactly. So, and the last thing that we control is basically the brakes, and I'm handing that over to Joachim to present the non-real-time part of the software.
Yeah. So I just need to say that I'm not, in case David watches this, I'm not technically the lead for the non-real-time part of the software anymore. I used to be the overall lead for all the software, but so I kind of designed the overall architecture of all of it, but David is the lead for the non-real-time software right now, just in case he's watching, so he doesn't kill me. So next slide, please. So this is, okay, so this is the pod, basically. And this is the ground station. This is our sort of NASA-style mission control that we're going to have. A bunch of monitors, you're going to have graphs and stuff. You see the velocity, you see the orientation, you see how all the hover engines are doing, the temperatures of a bunch of things. So, and how we get that. So this is the pod. These are all, oh, sorry, had some beer. These are the nodes that Marek was talking about. So each of these is a Raspberry Pi and a Teensy. And they all have, like I said, sort of different tasks. So, and between the RPod and the ground station, we have two different links. I don't know if you guys have learned about the difference of TCP and UDP yet, but you should, it's important. So, for command traffic, you want to, these are like sending commands to the pod, like start the pod, or like set this engine to that speed, or like brake, that's the important one. So, you want to use TCP, because then you have acknowledgements and you have guaranteed that the packets will be sent. So, it's more robust. But for telemetry, which is basically sending the numbers back that goes on the screen of the control thing, that goes across a UDP link, which is much faster, it has less overhead, but it's not as robust. You can lose packets and some data there, but it doesn't really matter if we miss a millisecond or two of data, because we're not going to have time to react in a millisecond anyway. It's going to explode if something goes wrong in that case. But we don't mention that. So inside one of these nodes, we have, I picked some bad colors now, I realize, but okay, so these are a number of different modules, and they each have different tasks. So you have something called a telemetry module, you have a command module, an update module, data store, this is a database basically. These are written in Python, most of it, except the data store, which I think will be in C. And they communicate between each other using a protocol called 0MQ, which is really awesome. You should all learn it. It's very good. I built telecom backends with it back in the day. It was fun. So yeah, so the telemetry module is basically responsible for sending, and all of these nodes as well, they talk across an Ethernet link. So basically your standard sort of IP thing. So the telemetry module sends the data across here. The data storage, also, but there's so much data that we can't really send all of it back. So most of it gets stored here, but like 10% of it or something like that, every 10th cycle, we send the telemetry back here. We have the command module that receives the commands from here. It goes like this, and then over there. So like the break command will go there, and then it's this guy's job to figure out, okay, where do I send this command and what do I do with it? We have the I2C module here, which is basically responsible for grabbing, imagine there's a Teensy here. Tom is laughing at me, stop that. But imagine there's a Teensy here, all the data gets sent over here, and then it goes over to, it gets sent over here, then it goes over to the data storage, gets stored there, then some of it gets sent over to the telemetry module, goes over the Ethernet link up here. Makes sense? Then we have the update module in case you want to update the firmware on the Teensy. So let's say we figure out a better control algorithm for the engines or something like that. Then we send the command over to this guy, and we send it a bunch of code, and hopefully that will get on the Teensy at some point. Not while we're driving the pod, that would be bad, but like when it's in storage or something like that. Yeah, so that's the software. Hope it made sense.
All right.
No, there's more. He's going to talk more. I don't think we're done.
Almost done. If you followed everything you hired. So back from software. So to build a pod, we had to get some funding. We ran an Indiegogo campaign, which was successful. We ran a 60K. We raised 60K. The company is still going, so we can still sell goodies and stuff. So if you guys want to buy stuff, go for it. Yeah. So we got that going, and we had basically, so as I told you, everything was done online. We never met anything to work, and we had to go from internet to real life. That's where T Connectivity came in and did a partnership with us. So they said, hey, we have a place in Menlo Park. It's about to get destroyed by Facebook. So in the meantime, you can have that place and just do your stuff over there, which was great. So we have that place now. So if if you guys want to check out the space at some point, just send us an email. I'll be happy to show you. So it's in Menlo Park, and we are building the pod right now. This is the place where the makers, the people basically everybody that's on the side is a maker. That's where we're doing all the stuff over there. Let me show you while I'll talk. Just a video of that's the test of our hover engine. That's the startup of our hover engine. You can see the pro going on, and then it's alive. So that's what the hover engine sounds like. And you can see in the bottom right, we have the pod coming to life, and people are working on it. As of right now, some people didn't come because they had to continue working. So there is a lot of work to do. So we are, the deadline, the final deadline is for end of January. That's when the competition is. We have another deadline end of October where we need to test some components. So a lot of stuff. We always need more hands. So if people are around and they want to give some hands over there, we are always happy for that. So crowdsource engineering, that's some closing remarks. Crowdsource engineering as of right now is mostly stuff like software, mostly, or companies that come with, oh, I need a logo, let's ask the crowd, and they kind of pick the best logo and pay that person. I think we showed with rLoop that you can do complex engineering R&D over the internet. So you can have a lot of people from all across the world working at the same time on a complex project. Where do you go from there? Well, imagine yourself if you had, 1,000 eyes looking at one problem. You can, and that's the way we've been doing the thing, you can either identify trends, okay, it looks like this is the way we should solve this problem, or you can have one guy saying, hey, actually, we didn't look into that thing. That could be a problem right there. So that's the power of having a lot of people working on it at the same time. Where do we go from there? Depends on all of you. Personally, that's the kind of stuff I like. They are maybe less software related, but interstellar travel, full electrical airplane, and asteroid mining. I'm an aerospace engineer, so that's really my vibe. But whatever you guys can think about, I really think with the tools we have nowadays, you can really make that happen. So thanks everybody for inviting us here, and I hope we did a good job at presenting what the rLoop is about. Thank you.
Okay, there we go. Now I cannot lose my voice. Perfect. All right. Are you guys having a good time so far? Yeah? Awesome. Yeah, I'm so stoked that we're actually I can't believe that I know these people and that we're really blessed to get to do the stuff that we get to do, all of us. If you're at Hack Reactor or wherever you are, it's such an exciting time to be alive. I'm not an optimistic person at all, so sorry for my cheesiness. But I do want to thank our sponsors tonight for hosting us. The first people I would like to thank so much for is Hack Reactor for giving us the space. That's awesome. Very cool. I want to thank the guys at Meta. They make a headset that you can put on. It's for augmented reality. And not only did they donate a $1,000 headset to rLoop that a gentleman by the name of Tyler Lindell and I will be designing and developing, but they also bought some of the beverages that you were drinking tonight. I hope everybody got a beverage. If you didn't, there is boxed wine, and why not? I'd also like to thank my company, Spacetime Insight, because my CEO, I just walked up and like, please, can we have some money so we can buy some pizza so people think this is cool? And he was like, sure. So big thank you to them, and thank you to rLoop. I don't know if everybody would be in the room tonight. Maybe there'd be 3/4, maybe there'd be half, but because you guys are here and you're doing this incredible thing, we're excited and we're here and we're behind you. And so thank you very much for making tonight what it was. Yeah. All right, so we're going to get to augmented reality now. I'm going to talk tonight about design. My background is user experience. I do a lot of 2D prototyping for geospatial analytics, and in my spare time, I do this. And I like to design augmented reality, and I've done some contract work, and it's okay. I have a lot to learn. I'm working in 3D modeling right now. I'm learning Unity 3D, and it's a blast. By the way, if you guys can pull out your phones, and or while you're ignoring what I'm talking about, just do a tweet real quick. We're at Hack Reactor, and it's a hashtag weird word, ARUX. So I want to be sure to mention the developer I'm working with. I'm going to show you a demo tonight, and what you're going to see is 90% he wrote it. And you know, it's just a low fidelity prototype, so you'll want to judge it with a grain of salt, because it's a user experience lean methodology that I'm using. We showed rLoop, this is what we can do, and they're like, whoa, cool. Now we're gonna make it look cool. But yeah, so Tyler Lindell, he is a software engineer, and he's dabbling in artificial intelligence. Some of the stuff is on GitHub. Super talented, rad guy. So let me tell you what we're gonna talk about tonight. I want to talk about the pain points of augmented reality. If you are doing anything, we should probably care about pain points, whether it's like web apps or you want to build a shovel or anything. You should think about the pain points that people are having when you're building a product, or else you're just a solution looking for a problem, which I hope is not what augmented reality is, because I sure love it. So I'm really instilling confidence, aren't I? I want to talk to you about some problems then. I want to find some problems for people that we can solve. So I found this picture online. This is the European Space Agency, and I think there's quite a few problems here. Now, these are the smartest people in the world, so they've designed some great things, but I'm trying to think far out into the future. And so I see some issues with their workflow as a user experience designer. And the next slide will point out what some of those are. But actually, I want to engage you guys and like use your imaginations, really think outside the box, and tell me, like, what are some problems that you see in this situation for somebody who's in a command center operating like spaceships? Keyboard confusion. Ding, ding, ding. You get $100. You get $100. No, I always wanted to do that. Keyboard. Nobody gets $100. Keyboard confusion. Anybody else? Yeah. They have to divert their attention between the information they're looking at and what? Yeah, they have to divert their attention between here and here. Perfect. Anybody else see anything? You can't be wrong. I'm not going to judge you if I'm wrong all the time. Yeah?
Yeah, I've worked in that position, and it gives you a wicked hand cramp.
Wicked hand cramp. Thank you. I want to do a user interview with you later. Thank you. What's your name?
Chris Phillip.
Chris Phillip. Thank you. Oh, yeah. This is a microphone that I can... Okay, I just want to throw this. I'm throwing this at you. What's your name?
I'm Connor.
All right, throw it back.
Here you go.
That's so I'm going to ask more questions tonight. This is great. Wow, you guys are engineers. All right. Okay, so yeah, we got that. Look at his back. Talk about like hand cramp. Look at his back. Like the reason he's hunching over is because these screens are recessed because of the keyboard confusion, and that's uncomfortable. The third thing is, look at this. This is 2D area right here that's holding information. What if there was more information in this screen? He has to fit everything in here because it's bound by this monitor. So depth. I think is an issue, and there's a phone here. Why is there a phone? You can just use your cell phone. But you know what? I just want to say the ESA, I mean, they're brilliant. I am not even 1/10 as smart as they are. And they're in the business of putting people in space, not fancy UX design. So I have a lot of respect for them. But I just wanted to point these things out. And we could find more. So now that I've showed you the operations center, I want to show you a demo for like how I might fix this problem. How Tyler and I envisioned it. And we contacted Meta and we're like, hey, can you donate a $1,000 headset? And they're like, yeah, why not? And then we called rLoop and they're like, do you want a $1,000 headset? And they're like, yeah, why not? So let me play this thing here, and hopefully this demo will work. We all know how it is when you go to start something and it doesn't. So this is going to be in Unity, right in C#, and then I used Blender and Photoshop to do some 3D modeling, but I'm going to be honest, I took the 3D models from some guy named like Tweet Pew Pew and other people from a website that I will put the name on here, so I'm giving them credit. But I changed the actual designs, and then the UI I made myself, like the cheesy hexagons. Okay, so augmented reality, by the way, is you're registering digital aspects in the physical world in your field of view. So things that you can never see in reality, you're going to see them through AR. So let me press play again. Sorry, guys. Oh, it hadn't pressed play. That's why. Perfect. Okay, so we don't have the headset yet, so I had to build it on the iPhone here, which is okay. Well, it is what it is. But we actually made it happen, and that's really exciting. So there's 3 screens here. There's the screen over here, and that's pod telematics. So you're going to have acceleration, velocity, pitch, and I don't know if you guys are using Jerk or not. I don't know if you have Jerks there. Probably not. That's a bad joke. I'm not a comedian. Then we have the pressure, temperature, charging UI here, and then finally there's the pitch and the yaw and the gimbal. And also there's going to be like a console like updates here, so they can go back and forth and look at these. And when we get to Meta, they'll be able to move these things with their hands as well. So. And then the final thing is we actually did do an actuator here. So, as you're looking, I mean, it's cheesy, but yeah, as you're looking, you can actually rotate what you want to look at. And this is our first stab at making some UI. And if you're into VR, AR, you'll see some of these design patterns around. So this is nothing that I actually invented, although I wish I could take complete credit for it. Okay. So that's kind of what I'm thinking might be a solution to the problem for somebody in the operator center, as in the operations center. And if you want to talk more about it, please email me, tweet me, and we can I'll just stay up late and we'll just talk about it because it's really exciting. But I have to stay on point here. I have to keep attention. All right. So I told you tonight's talk was going to be about the cognition behind augmented reality. And so I want to dive into the brain a little bit. And there's a lot of things we could talk about. There's memory, there's executive control, planning. But I think attention is really important for somebody who is working in an enterprise situation. And so I want to explain to you what attention is and how it's going to impact the designs that you're going to code, that you're going to push pixels on. However, so this is a 3D model of the brain that I was telling you about, in case you haven't figured it out yet. And there's 3 parts of attention. Okay, so attention really isn't just your mom telling you, "Hey, pay attention." You know how to pay attention. And you're like, "Oh, okay, I'm going to focus really hard." It's actually comprised of 3 different regions in your brain, and these 3 different regions are responsible for 1, selecting, 2, orienting, and 3, alerting. So 3 separate regions respectively assigned to these three things. Selecting means choosing among conflicting actions. So you're out, you see UI, like maybe there's like a bunch of UI in front of you, and you have to select which one that is relevant to you. Orienting is referring to a point of reference to sensory objects. So that's actually, it's not selecting. You're actually moving, your thoughts. You're moving your attention onto an object. And then finally, alerting. Alerting involves changes in the internal state and preparation for perceiving a stimulus. So something's actually happening in your brain. Something happens. There's a stimulus like that, grabs your attention, and there has to be some physiological change in the neuronal array in your brain. So I wish I had time to talk about all three of these, but I don't. So I'll talk about the orienting one predominantly, but I wanted to show you a video that is kind of funny about attention or not paying attention. So this is a guy who's going to run into a window. Let's watch it. Well, I got to press play first. Sorry. I am really smooth at these presentations. He actually handed me a clicker earlier. This is all getting... All right, there we go. This is great. Look at that. This makes me feel better about my life. So I'm going to ask you guys a question, and I get that box. This is going to be great. All right, so why did he run? Why did he run into this is like a bad joke. Why did he run into the glass wall? Do you think he was having issues selecting? Do you think he was? Does that question make any sense, or is it just like, what are you talking about? Well, we'll see here. If it clicks for anybody. If not, I'll try to explain some more. If not, I'll move on in embarrassment. So the first one is he selecting? Is he having a problem selecting like his attention with what he needs to do? Like, is he having an issue orienting himself in space, or is it an alerting thing? Like, for instance, this door. Like, is it his fault he ran to the door, or did the people who designed it not alert him that there's a door here through some simple means? I know it's a dumb question, but if they would do it right, then maybe he wouldn't run into the door. So, what do you guys think? Not knock off your beer there. What's your name?
John.
John.
He wasn't paying attention. It's alerting.
Alerting. Very good. Okay. Anyone else have an opinion? I'm not going to correct anybody here. I just want to hear what you think. That's all.
I would need the microphone. I would say the foundational problem is number one, selecting. He looked up and said, I can go left or right. He didn't recognize that was not a transmissible area. He thought he could pass from either side, and therefore he oriented himself and didn't bother to alert himself. He made a mistake in step one saying, I can walk through that thing.
Yeah. Cool. Okay, so you say it's alerting. His mind wasn't alerting something. You say it's selecting. He wasn't selecting what he needed maybe to pay attention to. Anybody else? I can throw this thing really far. I can. Okay, we'll move on from that then. My personal opinion on it, and I'm not a neuroscientist. I have an undergraduate degree in cognitive science, but that means I just know how to read stuff and kind of put two and two together. So I think his attention was on time and it wasn't on space. Like, he's looking at his phone. As a UX designer trying to read somebody's mind, I think that his mind was like on an appointment that he had to get to or something, and so he wasn't able to orient his attention. I think orienting was the issue, but it's kind of relative, and some PhD could walk in here and tell me the real thing. But so there's two parts of orienting. There's a cue, like, hey, I snapped my fingers, or I jumped really silly, and you're like, whoa, that happened. Or there's a voluntary control where you're actually going to divert your attention somewhere. So those are the two parts of orienting, and so we look at things that interest us and that relates our attention to where we fixate. I think that's part of voluntary control. I think this guy decoupled his attention from where he was looking at. He was attending some cue, maybe lunch, other than the center of his gaze. His action of hitting the glass shows that he was sensitive to information occurring with respect to where he was putting his voluntary control. And I think he was relatively slow to have information move across his fovea. So all orienting happens in the parietal lobe. So there's 4 parts of your brain. There's the frontal lobe. You have your visual cortex in the back, temporal lobe, and then up here is like kind of this area is where parietal activations happen. I just think this stuff is interesting. Let's see here. Okay, so let's get to the augmented reality and see how all the stuff that we're talking about actually applies to this. So I put these purple dots here to draw, like to show a UI element that you might orient yourself to. So this is the UI that you saw in the Hyperloop demo, and I think with augmented reality, there's going to be a lot of things happening around you, and it's going to be a complex task to orient yourself. So I think that we need to create interaction models that are going to accommodate for that. It's going to take a little bit of artificial intelligence and machine learning to predict you and where you're going to look. So this is an interaction model that I think may work, and I'll try to explain it to you. So you know all these UI elements, a couple slides back, like you saw the map, you saw menus, so on and so forth. Well, let's say that they're represented here by, here's one object, here's another object, and here's another object, and you've got your headset on, and as you move that accelerometer, then an object of interest is there, and I'm suggesting it expand when you look at it. But you don't want everything expanding like right when you look at it, because then that would make you nauseous. Things would be blowing up everywhere, and that would not be good. But you could use the inverse law found in physics, like for gravity. As something moves closer to another object, it'll start to accelerate faster and faster, and you can vary the rate of acceleration at which this expands as a function of time this guy's looking at it, and conversely shrink these. And so this is an idea that I have. It might not be good, like Tyler and I might make it on the Meta headset, and turns out that it's not, but we can test it. And that's the beauty of science, is that we can do an experiment to see if it objectively works or not. This talks about designing for the attentional blink. I think this video is pretty interesting, actually. This is going to talk to you about how you can actually miss targets or UI elements that are happening in your vision. So I'll let the video explain how that works. Pay attention. It's kind of fun. Can everybody see it okay? And then they're going to do some promotion for their company for making a really cool video, and I'm going to take it off of that. Sorry, guys. Who succeeded at catching both the targets? You did, Alex? You're like superhuman. I didn't even see one. Just joking. Who else got both of them? Anybody? You got both of them? You got both of them? Very cool. Who got one? A lot of people here got one. Very cool. I mean, that's just an example of all the things there are that happen in human perception that when we leave designing in 2D space, we're going to have to account for. We're going to have to design and code for. So making augmented reality is going to be very complicated, and I'm glad there's a lot of smart people in this room who are able to do it. So I'm done with that talk. I'm going to wrap up with you guys. So here's the deal. This is the first augmented reality hacker or hack AR. We should vote on how we say it. I don't even know. But what it's going to be from now on is we're going to hack together. We're going to have speakers come for like 10, 15 minutes and present on something, and the rest of the time we're going to be making things. So there's going to be a prize. The first one's to be decided. We just got some funding, so we'll try to find something cool. If you guys have any ideas, email me or tweet me. It's somewhere probably in the $50 range. I have to create the judging criteria for it, but that's what you can expect at the next Hack Reactor. After this, we're going to get some beer. I didn't get any beer. It's probably good that I didn't. Perhaps you think I did. I don't know. Or something, but I didn't. So anyways, I think that's it. So I'd like to thank everybody for coming out, and I hope that you'll come to the next event. Did you have a question? Oh, thank you so much. Thank you. Yes. So Q&A. Does anybody have a question for the rLoop team? Something like piqued your interest or something I said? We'll get to both of you. Yeah, go ahead. Here. Sorry, here's the microphone.
So what happens if the pod flips over? I see wheels on one side. Is there wheels on the other side?
Next question.
That's a good answer. So it's actually really not physically possible for the pod to turn over because it's kind of riding the I-beam. If we do turn over, it means that a lot of other stuff blew up before that. So we are.
And we have other problems to worry about. Yeah. Elon will definitely be mad.
So you have a lot of sensors that are throughout the entire machine. Do you have any backups, or do you have any backup plan in case one fails?
So we don't have not every single sensor has a redundant counterpart, but basically we have accelerometers, like 3 of them, and we theoretically need only 1 of them, so we will make them vote. So if there are 2 that agree on the value, we say like these are good. The same goes for the contrast sensors, but that's basically it. The thing is that the full redundancy is difficult, so we just focus on trying to make the system as robust as possible and not trying to implement the full redundancy because we just don't have time for that.
What about the brakes?
What about the brakes?
So the brakes are extremely. This is the most important part of the system because the way we get to speed, we are being pushed. So we don't have to worry about proportion, right? All we have to worry about is about braking. So the brakes are, you have those. If the power shuts down, if anything goes wrong, you have those huge springs that will force the brake to engage.
So there's
worst case scenario.
There's a fail-safe mechanism. So in terms there's no power, the brakes will still engage.
Yeah.
Basically, you have electrical motors actively pulling the brakes away from the I-beam, so we need power to be able to move the pod. It's the same thing you have on a truck, basically, but with compressed air and stuff.
But you still need to push anyway, so you have those springs that are loaded for the system. But yeah, and the nodes themselves for the brakes, the nodes are redundant. So really, this is just a big braking pod.
So for instance, the control system for the brakes is redundant as well. So, but that's like the only one. So if there's something that we should be able to do is to brake. and we'll steer not sure. I mean, we're sure. But
and to write on your first question regarding redundancy, even if we lose some of the sensor, we can still kind of guess some of the stuff based on the other sensors. We have, for example, a laser rangefinder that is in the front of the pod that will be kind of, there is a wall at the end, so that will kind of, when you get in range, you'll see the distance you are from that. But based on the accelerometer and so forth, we can kind of tune the data, so know where you are approximately, so you can kind of overlap some of the stuff like that. That gives another layer of verification if your sensors agree or if something's going wrong.
exactly. So a lot of voting between the sensors.
We also have 2 battery packs.
Right, I'm sorry.
The whole system can
yeah.
run only on one battery pack. So we are, if one battery will have to fail, hopefully it doesn't fail in like thermal runaway, which is just means the pod goes in flame. If it's just like, oh, something doesn't work, we can just have the other battery pack working. So we have a lot of redundancy of the thing.
Yeah, but the point is not everything is redundant.
Yes, sir.
Well, I don't know how to frame this question, but I'm going to try anyway. Have you ever been on the Coast Starlight?
I don't believe so.
Goes right down the coast of California,
Oh, yeah, yeah.
Santa Barbara.
Uh-huh.
And you get to LA, it takes about 8 hours, but you're seeing California. Have you done any psychological NASA type simulations? It's going to be like
That
be in a horizontal elevator, basically closed off, going 700 miles an hour for 35 minutes. God bless you for doing it. And is there any possibility that AR or VR for the participants, so they have some sense of where they are, might help?
So, 2 answers for that question. Regarding the, you can see some stuff out there. You can kind of think the train you mentioned, like taking the one along the coast, and already taking the 5, you just want to go to LA, and you don't care about the things, you just want to get there. Regarding AR, VR, it's very important to have, and it's not a study we've really been done, but we looked at those things. But yes, it's important for a person inside to not feel like they are in a big coffin going at very high speed, right? So
In a vacuum.
we always thought about, since the beginning, having everybody will have a VR headset or something, and they will be able to see outside or look at something. And so I think it's very important for that, yes.
Yeah, just to follow up quickly on that. So the ride is going to be very quick. That's the first thing. Secondly, basically, you can think of that ride as being in a train and in a tunnel. That's going to be just the same thing. And in terms of the velocity, I mean, it doesn't really matter if you go 100 miles per hour or 1,000 miles per hour, because if there is no change in acceleration, for you, it's basically the same sensation.
But there are people doing a lot of research into the sort of augmented reality windows and stuff that you could have on the pod. So maybe you would sort of film the whole path that the R pod would take, and then you can sort of project that on a like fake window inside the pod or something like that, and then you could have like motion or head tracking, so you figure out where the passenger's head is, and then you adjust the sort of perspective on the window.
There's a lot of different stuff we can try. Yeah.
It's software. I'm talking software.
No.
They like that. So, yeah, how about you do it?
Oh, I'm gonna try.
That's a good question.
I'm gonna try. Me and Tyler are gonna try to do it. Yeah. Any other questions?
It sounds like you guys did a lot of your sourcing from sort of consumer materials. What are some of the biggest challenges that you've had dealing with that? Like, it sounded like accelerometers is one.
Well, I would say the biggest challenge you have is that that people don't get paid in the project. You have no leverage over people. So if you can't say that
now,
yeah,
for everybody, what are you doing here?
well, so like you can't say that you have to have this done at that time or you don't get paid, because he's not going to get paid. Yeah. So you have to kind of assume that any one person can leave at any time, and you basically